Happy morning, friends. In today's class, we are going to see about the programming input and output. So, the basic technique for input-output programming can be understood relatively independent of the instruction set. So, we will begin by discussing the basic characteristics of input-output device so that we can understand the requirements they place on the program and how the devices are communicating with them. So now let us see about the input-output device. So this diagram represents how the CPU is communicating with other register. So the CPU is talking with the other devices by reading and writing through the registers. So here the data register holds the value which is considered to be a data. Then the status register provides the information about device operations, such as whether the current transaction has been completed or not. Some register may be read-only, such as status register that indicates when the device is done, while others may be readable or writable. Then the next one is the input-output primitives. So the microprocessor can provide programming support for input-output in two ways. One is input-output instruction, another one is memory mapped input-output. So you know that what is input-output instruction. So by handling the registers, we are passing some instruction to access our input-output. That is called input-output instruction. In the case of memory mapped input-output, it provides the addresses for the register in each input-output device. So the program uses the CPU's normal read and write instruction to communicate with the devices. Then we are going for busy wait and input-output. So typically all the peripheral devices are slower than the CPU. So it requires multiple cycles to complete its operation when it is compared to the CPU. The CPU is performing multiple operations on a single device, such as writing several characters on an output device. So then it must be wait for one operation to complete before starting the next one. So that signal is called busy and wait input output. So here, for example, if you are taking, we are trying to start the second character before the device has finished with the first one. The device will probably never print the first character. So always whenever our input output devices are whether it is completing its operation or what, we know the status by reading the status register. It is often called as the polling of the register. So the next one is interrupts. Always the busy wait input output is extremely insufficient because the CPU does nothing but test the device status while the input output transaction is in progress. In many cases, the CPU could do the useful work in parallel with the input output transaction, such as it may do the computation or determining the next output to send to the device or processing the last input received or controlling the input-output devices. So here the interrupt mechanism allows the device to signal the CPU and to force the execution of particular piece of code. So when the interrupt is occur, the program counter value is changed the pointer to the interrupt handler routine. So that take care of the device. So in this diagram, the interface between the interrupt mechanism has been shown. So whenever the input-output devices send the request for the interrupt, the CPU will check for the interrupt priority and it will send back to the interrupt acknowledge. So whenever it releases the interrupt acknowledge, the CPU will not further fetch the address from the program counter. The program counter address is stored in the stack, temporarily stored in the stack. Now the CPU will fetch the address of the interrupt handler. So here the interrupt handler address will allotted as some subroutine. So the CPU will execute some piece of code as a subroutine. After executing the subroutine, again the CPU will fetch the program counter address from the stack, and further it will execute the foreground program. So here the foreground program is the program that runs when no interrupt is being handled, is often called as a foreground program. So whenever the CPU completes the interrupts, it will go to the foreground program again. This is about the interrupt mechanism. Then the priorities and vectors. So how the different input-output devices or some external devices giving multiple interrupt signal to the CPU, how the CPU will handle it. So here the device 1 will generate some interrupt, device 2 will generate some interrupt, and device N will generate some interrupt. So instead of giving interrupt technology to all the devices, it will check the interrupt priority. So whichever devices got the highest priority, that interrupt is called the non-maskable interrupt. So that interrupt cannot be masked, so it has to execute immediately. So the CPU will send the interrupt, instead of sending the interrupt acknowledge, it will send the priority number as a acknowledgement, so that the device can understood that my priority number is in the line, so my device is got acknowledged, so that the address of that particular subroutine has been executed by the CPU here. So these are some of the interrupt vectors. So here the CPU, and there is an external device. The external device is requesting for the interrupt, and whenever the device get acknowledged, the same device will send the vector handler to the CPU. So based on the vector handler, the CPU recognize the vector number. So from this vector number, it can able to search the interrupt vector table on which handler it has to execute. So for example, if the vector is sending number 3, so that is the vector number. So based on the vector number 3, it will fetch the handler 2. So this handler 2 holds the address of the interrupt where it can start the execution. So based on the address, the CPU can start the execution of handler 2. So this is about the interrupt and priorities and vectors of the ARM processor. Thank you.